Centuries ago, builders created monuments that still tower over us. They worked without any of the machines we depend on today, relying on brilliant minds and simple tools. This journey reveals 20 incredible medieval engineering marvels and the forgotten secrets behind their construction. You will discover how our ancestors achieved the impossible, from cathedrals that scrape the sky to castles that could not be taken. How did they move stones heavier than elephants or design clocks that tick for 600 years? What does their genius tell us about our own modern world? To call the medieval era a dark age is to ignore the brilliant light of its engineering. This was a time of profound innovation, where builders worked with a deep, almost intuitive grasp of physics and geometry. They did not have our modern materials, but they mastered what they had: stone, wood, and simple lime mortar. Their greatest tool was knowledge, carefully guarded and passed down through generations within guilds of master craftsmen. These men understood the strength of an arch, the distribution of weight in a vault, and how to cut stone so precisely that it locked together without any need for modern cement. This foundational expertise transformed ambitious dreams into permanent reality. Consider the sheer scale of the workforce: thousands of skilled and unskilled laborers working for decades, sometimes even centuries, on a single project. This long-term vision, this commitment to a future they would never see, is what allowed them to create structures that still define our skylines today. With this backdrop of immense skill and patient labor, the true scale of their achievements comes into sharp focus. Rising from the heart of Paris, Notre-Dame Cathedral remains an enduring symbol of human aspiration. Its construction began in the year 1163, a project so ambitious it would take nearly 200 years to complete. At the core of its revolutionary design were the flying buttresses, those graceful stone arches that leap from the outer walls like bony fingers. These were not mere decoration, they were a structural masterstroke. By transferring the crushing weight of the heavy stone roof and vaults outward and down into the ground, these external supports allowed the walls to be built higher and thinner. This genius innovation made space for the cathedral's most breathtaking feature: its enormous stained glass windows. For a medieval worshipper, stepping inside was like walking into a kaleidoscope of divine light, a radiant glow made possible by pure engineering. The cathedral's stone skeleton was a puzzle of incredible precision. Master masons, working without laser levels or computer models, used simple compasses and squares to lay out complex geometric patterns. Each block of limestone was hand-cut to fit perfectly with its neighbors, locked together by gravity and skill alone. High above, another wooden wonder was taking shape. The roof framework, nicknamed the Forest, was built from over 1,300 oak trees. Each massive beam was meticulously shaped and joined using wooden pegs, a testament to the woodworker's art that withstood the centuries. The devastating fire of 2019, while tragic, revealed a hidden truth about this medieval marvel. As the world watched in horror, the burning roof collapsed inward, but the stone vaulting beneath it largely held, protecting the interior. This survival was not luck. It was a direct result of the original builders' profound understanding of load distribution and material strength. Notre-Dame stands, even in its wounded state, as a powerful lesson in resilience. It shows us how Gothic architects dared to reach for the sky, using stone and light to create the impossible. This drive to build higher and brighter would inspire even more daring structures across Europe. Far from the soaring cathedrals of Europe, another kind of medieval marvel was taking shape: one that snaked across mountains and deserts on a scale almost impossible to comprehend. The Great Wall of China, particularly the sections massively reinforced by the Ming Dynasty, represents a different kind of genius, one of logistics and endurance. While earlier walls existed, the Ming builders, working from the 14th to the 17th centuries, undertook a project of staggering ambition. They were not just building a wall, they were constructing a continuous fortified border thousands of miles long. How do you even begin to manage such a task without modern machinery or communication? The answer lay in an immense, organized human effort. Millions of soldiers, peasants, and prisoners formed the backbone of this endeavor, moving materials across impossible terrain. In the rugged mountains, workers quarried local stone, while in the plains, they perfected the use of tamped earth, compacting soil and gravel between wooden frames to create sections of incredible durability. Bricks, a technological advancement of the time, were fired in kilns built right on site. Transporting these heavy materials up steep ridges was a Herculean task, accomplished through human chains that passed bricks hand over hand, or with the help of donkey trains navigating narrow paths. But the Great Wall was far more than just a physical barrier. It was an integrated communication system. Watchtowers were strategically placed within sight of each other, often on the highest peaks. From these vantage points, sentries could send messages across vast distances in a matter of hours. A single beacon fire or a column of smoke could relay a warning from the farthest frontier deep into the empire, a medieval internet of light and signal. The wall's resilience is another testament to its brilliant engineering. Builders did not simply lay foundations on top of the soil. They often dug down to the very bedrock, creating a stable base that has resisted centuries of earthquakes and erosion. The wall itself was built with a sloping profile, wider at the bottom and tapering towards the top, a shape that effectively distributes stress and sheds water. This was not a static wall, it was a living, breathing organ of defense, designed to withstand both the forces of nature and the onslaught of armies. It stands as a monument to the power of adaptation, showing how medieval engineers solved the unique problems of every landscape they encountered. Its famous flaw was actually a triumph of medieval ingenuity. The Leaning Tower of Pisa began its life in 1173 as a grand bell tower for the city's cathedral. From the very start, its foundation was a problem, built on soft, unstable ground of clay, fine sand, and shells. By the time builders reached just the third floor, the structure had already begun to sink unevenly into the earth. Faced with a potential catastrophe, they made a brilliant and patient decision. They stopped building entirely. For nearly a century, the unfinished tower was left alone, a silent, tilting stump. This long pause was not an admission of defeat. It was a strategic move, allowing the waterlogged soil to slowly compact and settle under the weight. When construction finally resumed, the new generation of engineers saw the problem not as a failure, but as a puzzle to be solved. They observed the precise angle of the lean and began a delicate correction. As they added new floors, they deliberately made the walls on the sinking southern side just a little bit taller than those on the north. This subtle compensation, a crude but brilliant form of medieval counterbalancing, forced the structure to grow vertically, even as its base continued to sink. The tower's elegant cylindrical shape and hollow core were not just aesthetic choices, they were critical weight-saving measures, reducing the load on that treacherous ground. Despite its famous list, or perhaps because of the ingenious corrections made to manage it, the tower has withstood the test of time for over 800 years. It has survived numerous earthquakes that should have toppled such an unstable structure. Why did it not fall? engineers now believe the secret lies in the dynamic interaction between the soft soil and the rigid marble tower. During a quake, the tower does not resonate, it simply shifts without collapsing, a phenomenon known as dynamic soil structure interaction. The Leaning Tower of Pisa stands as a monument not to perfect planning, but to brilliant adaptation. It proves that the greatest medieval engineering was not about avoiding mistakes, but about having the wisdom and creativity to fix them. While the Leaning Tower stands as a testament to correcting nature's flaws, other builders sought a more harmonious relationship with the elements. High on a fortified hill in Granada, Spain, the Alhambra Palace was not built to defy its environment, but to embrace it. This sprawling complex, the crown jewel of the last Muslim dynasty in Spain, transformed a dry, rocky outcrop into a lush, water-filled paradise through sheer hydraulic genius. The lifeblood of the entire palace was a sophisticated network of canals, known as acequias, that channeled ice-cold water directly from the Darro River miles away. This was not just plumbing, it was a circulatory system that brought both survival and sublime beauty to every corner of the fortress. Water flowed through open channels, cascaded into serene reflecting pools, and danced in fountains, creating a constant, cooling melody. This mastery over water reached its artistic and mechanical peak in the legendary Court of the Lions. Here, a central fountain is supported by 12 sleek, white marble lions arranged in a perfect circle. But these were not merely decorative sculptures. This was a functioning water clock, an intricate machine of stone and liquid. The system was designed so that water would spout from a different lion's mouth each hour, marking the passage of time for the court in a silent, elegant spectacle. The engineering behind this feat required an incredible understanding of hydraulics and precise water pressure, all achieved with gravity alone. The marvels continue overhead, where the ceilings explode into breathtaking complexity. Master artisans, using nothing more than chisels and handmade drills, carved thousands of tiny, cell-like niches into the plaster and wood, creating a mesmerizing effect known as Muqarnas. This honeycomb vaulting appears to drip from the ceiling like frozen starlight, a geometric miracle that seems to defy the solidity of the materials. Every surface is a tapestry of interlocking patterns, a visual representation of an infinite universe, all laid out with a compass and a steady hand. The Alhambra was conceived as a complete, self-sustaining world. Its gardens were not separate from the architecture, but an integral part of it, cooled by the same water that supplied its baths and fountains. This seamless fusion of art, science, and nature created a microcosm of paradise on Earth, a revolutionary concept that would eventually ripple through European design. It stands as a powerful reminder that the greatest engineering does not always conquer nature, but sometimes invites it in to create something truly magical. Deep within the tranquil English countryside, a silent, ticking heart has marked the passage of time for over 600 years. Salisbury Cathedral is home to the world's oldest working mechanical clock, a device built around 1386 that still functions today. This clock is a monument to metal, not to aesthetics. It has no dial, no hands to point to the hours. Its sole purpose was to ring a bell, a single, resonant note that would echo across the town, ordering the daily life of a medieval community. The genius of this machine lies in its iron bones. Forged by an anonymous blacksmith, its intricate system of gears and levers operates without a pendulum, a technology that would not be invented for centuries. Instead, it uses a primitive but brilliantly effective mechanism called a verge and foliot escapement. This device controls the unwinding of the clock's weights, converting a steady fall into a series of measured, ticking motions. Each gear tooth, each handmade iron frame, had to be calculated with astonishing precision to keep a reliable rhythm, a testament to a blacksmith's deep understanding of ratios and friction. While the clock measured time, the cathedral that houses it seems to defy it. Salisbury was erected in a breathtakingly short span of only 38 years, a rarity for such a monumental project. This rapid construction gave it a unique visual harmony, a pure example of early English Gothic style where every arch and window speaks a unified design language. Its most famous feature, however, was a later, daring addition. The towering spire, the tallest in all of Britain, was not part of the original plan. Adding such a colossal weight to the top of an existing structure was a tremendous risk. Medieval engineers responded with a hidden skeleton. Inside the stone pillars, they constructed a reinforcing framework of great timber beams and iron braces, a secret internal scaffold that has successfully carried the spire's burden for centuries. This cathedral is a perfect duality of engineering minds, one focused on the celestial ambition of stone reaching for the heavens, the other on the precise, earthly science of measuring moments. Together, they prove that the medieval mastery of space was perfectly matched by a growing command over time itself. Half a world away from Europe's cathedrals, a different kind of monument was taking shape in complete isolation. On the remote island of Rapa Nui, master carvers created the massive Moai, towering stone figures that stand as silent guardians of a forgotten past. Between the years 1250 and 1500, this society achieved an engineering feat that seems to defy logic, carving nearly 1,000 statues from a single volcanic crater. The material itself was a key to their success, a compressed volcanic ash called tuff that was firm enough to hold detail but softer than granite, allowing them to work it with simple hand tools known as toki. These were not crude rock hammers but expertly crafted basalt picks that could be resharpened again and again, letting artisans chip away at the mountain with patient, deliberate strokes. The largest of these figures, nicknamed El Gigant, was never fully separated from the quarry, a colossal giant that would have weighed an almost unimaginable 270 tons. But even the average Moai, standing over 20 feet tall and weighing more than 80 tons, presents a monumental puzzle. How did a society with no wheels, no draft animals, and no metal move these giants miles across rugged terrain to their coastal platforms? For decades, the dominant theory involved an army of workers laying down a path of logs as rollers, slowly inching the statue forward in a Herculean effort. Another compelling idea, one that seems to breathe life into the stone, suggests the islanders made the statues walk. In this method, teams would use ropes to rock the Moai from side to side, carefully edging it forward in a controlled, upright shuffle. This theory is supported by the statue's distinct design, with their forward-leaning center of gravity and rounded bases that appear perfectly shaped for such a rocking motion. Recent experiments have shown that with 3 teams of ropes and a skilled coordinator, a replica Moai could indeed be walked hundreds of yards in a day. This was not brute force, but a symphony of coordinated effort and a profound understanding of balance and physics. Once at the coast, the statues were raised onto their stone platforms, known as ahu. These bases were feats of engineering in their own right, built with such precise stone fitting that you cannot slide a blade between the rocks. This technique, reminiscent of the finest Inca masonry, provided a perfectly stable foundation for the multi-ton figures. The entire process, from quarry to platform, was a breathtaking demonstration of communal will and clever problem-solving. The Moai are more than just stone faces. They are a powerful reminder that human ingenuity is not dependent on outside contact or advanced technology. In total isolation, a medieval society conceived and executed a plan to rearrange their very landscape, leaving behind a mystery that continues to challenge our assumptions about the past. Perched high on a solitary hill in modern-day Syria, the Krak des Chevaliers was more than a castle. It was a statement of absolute power. Built and expanded by the Knights Hospitaller over the 12th and 13th centuries, this fortress represented the peak of medieval military engineering, a concentric design so formidable it was considered virtually unconquerable. The secret to its strength was not one wall, but many. An attacker who miraculously breached the lower outer wall would find himself trapped in a deadly killing ground, exposed to a hail of arrows and stones from the higher inner walls that loomed all around him. This layered defense meant every inch of ground was covered by overlapping fields of fire, turning the castle itself into a massive stone predator. Even reaching those walls was a near impossible task. The castle's base was protected by a massive talus, a thick, sloping skirt of stone that served two brutal purposes. It forced siege towers to stop at a distance, rendering them useless, and it deflected the blows of battering rams, causing them to slide harmlessly off the angled surface. But the true genius of Krak des Chevaliers lay in its ability to endure. It was not just a fortress, it was a self-sufficient city in stone, designed to withstand a siege that could last for years. Vast storerooms were carved into the rock, capable of holding enough grain, oil, and salted meat to feed a garrison of 2,000 soldiers for half a decade. Its survival depended on one crucial resource: water. The engineers designed an ingenious system to capture every drop of rain that fell on its sprawling roofs and courtyards, channeling it through stone gutters into massive, vaulted cisterns lined with waterproof plaster. This ensured that even during the driest summer, the defenders would never thirst. The castle's strategic position on a key trade route gave it a stranglehold on regional commerce, making it the ultimate medieval gatekeeper. For centuries, it stood as an unbreachable bastion, a masterpiece of defense where every stone was placed with a singular, calculating purpose: to outlast, outsmart, and overwhelm any enemy foolish enough to challenge its walls. While the Krak des Chevaliers mastered the art of holding water within its walls, another ancient structure performed the opposite miracle, moving water across a vast landscape. The Pont du Gard aqueduct in southern France is a monument of such perfect proportions it seems to have grown from the river valley itself. Though built by Roman engineers in the 1st century, its true legacy was secured in the medieval era as generations of builders maintained and used it, preserving a masterpiece they could not yet replicate. This was not a ruin to them, but a vital, functioning piece of infrastructure, a lesson in stone that stood for over 1,000 years. Its construction defies belief, a triple tier of graceful arches built entirely without mortar. Each massive limestone block, some weighing as much as 6 tons, was hand-cut to such a precise fit that it locks into its neighbor by gravity and friction alone. How did they lift these stones so high over the rushing river? The answer lies in human-powered cranes, immense wooden wheels turned by teams of men walking in a circle, slowly winching each block into its perfect place. But the aqueduct's most stunning feat is one you cannot even see, a slope so gentle it is almost imperceptible. The channel at the very top descends only 1 foot for every 3,000 feet it travels. This minuscule gradient was calculated with breathtaking accuracy, allowing water to flow from its mountain source all the way to the city of Nemesis, modern-day Nims, with just the gentle, unending push of gravity. A steeper drop would have eroded the channel walls, while a flatter one would have let the water stagnate. This was engineering as a precise science, a balance achieved with simple tools and profound understanding. Throughout the medieval period, the aqueduct did not sit idle. It continued to deliver fresh water, a lifeline for the communities that lived in its shadow. Its sturdy lower arches were even converted into a heavily fortified toll bridge, a testament to its enduring strength and strategic value. Medieval lords recognized a good thing when they saw it, and they protected this Roman marvel, ensuring its survival long after the empire that built it had faded into history. The Pont du Gard stands as a direct challenge to the idea of a dark age. It is proof that medieval engineers were not just innovators, they were also preservationists, learning from the giants who came before them and keeping the flame of knowledge burning bright. This reverence for ancient technique would soon fuel a new wave of construction, one that sought to build not just with stone but with light itself. But the ambition to build a perfect dome would find its ultimate expression not in the West, but at the crossroads of the world. In the ancient city of Constantinople, now Istanbul, the Hagia Sophia achieved a miracle of balance that would define a skyline for 1500 years. When the Byzantine Emperor Justinian first entered the completed church in the year 537, he is said to have whispered, "Solomon, I have surpassed you." He was not exaggerating. The heart of this achievement is a central dome of breathtaking scale, spanning 106 feet across. The genius of its construction lies not in the dome itself, but in the four curved, triangular sails of masonry that support it, known as pendentives. These ingenious structures act as a perfect transitional layer, gracefully converting the square base of the main building into a stable circular ring for the dome to rest upon. It is this innovation that creates the cathedral's most magical effect, making the immense dome appear to hover weightlessly on a halo of 40 windows, flooding the cavernous interior with an ethereal, heavenly light. The builders knew that such a vast stone dome would generate immense outward thrust, a force that could push the supporting walls apart and cause a catastrophic collapse. Their solution was one of brilliant foresight. They constructed the dome not from heavy stone, but from specially manufactured bricks, crafted from a unique, porous clay found on the island of Rhodes. These bricks were remarkably light, yet incredibly strong, drastically reducing the overall weight of the structure. To build with even greater speed and stability, they developed a revolutionary mortar that used crushed brick dust, allowing it to set almost as hard as the bricks themselves. This rapid curing meant that each new ring of the dome would quickly become a single, solid unit capable of supporting the next. This foundational strength, locked in place over a millennium ago, is what allowed the structure to evolve. After the Ottoman conquest of 1453, the new rulers recognized the building's profound structural integrity. They added 4 slender, towering minarets to its corners, not as mere decoration, but as strategic buttresses that further anchored the building against earthquakes. The Hagia Sophia is more than a building. It is a living lesson in architectural physics. Its revolutionary use of pendentives and light materials represented a quantum leap in engineering, a formula so successful it would go on to inspire every great Ottoman mosque that followed. It stands as a permanent bridge between empires, a testament to a single, perfect idea that changed the face of architecture forever. While the Hagia Sophia redefined the heavens with its dome, another marvel was busy harnessing the power of the earth itself. In the remote village of Nashtifan, Iran, the wind has been put to work for over 1,000 years. Here stand some of the oldest windmills in the world, their vertical axles turning relentlessly in the fierce 120-day wind that gives the region its name, a name that poetically means storm's sting. These are not the familiar post mills of Europe, but a far older and brilliantly simple design. Built entirely from clay, straw, and wood, they are a perfect fusion of local material and elemental force. Their genius lies in their fixed vertical axle. Unlike European mills that must be turned to face the wind, these Persian sails catch the breeze from any direction. The wind pushes against bundles of reeds fixed to the central column, setting the entire mechanism in a horizontal rotation. This motion is then transferred through a series of wooden gears to turn a heavy millstone inside the mud brick tower, grinding grain into fine flour. The entire system is a masterpiece of appropriate technology, using nothing that was not available locally and requiring no complex moving parts that could easily break. For centuries, the knowledge of their construction and maintenance was not written down in books, but passed directly from one generation of millers to the next. These custodians understood the precise angle for the reed sails and the exact consistency of the clay mortar needed to withstand the constant, punishing gales. This was not a technology imposed on the landscape, but one that grew from it, a direct response to a specific environmental challenge. The Nashtifan windmills are a stunningly early example of sustainable energy, a medieval community running its daily life on a clean, renewable resource. They stand as a quiet, enduring testament to a different kind of engineering intelligence, one that sought not to dominate nature, but to listen to it and collaborate, creating a legacy of power that is both ancient and utterly modern. High on a sun-baked mesa in the American Southwest, an entire civilization turned the very rock into a home. The cliff dwellings of Mesa Verde, built by the Ancestral Puebloans between the years 1190 and 1260, are not just buildings tucked into a cave, they are a masterpiece of communal engineering carved into a sheer sandstone cliff. To construct these multi-story villages, builders used the cliff itself as a foundation and a back wall. They quarried blocks of sandstone directly from the site, shaping them with harder stones before setting them in a simple but effective mortar made from local soil, ash, and water. For floors and roofs, they fitted long wooden beams into holes chiseled deep into the cliff face, a framework that has held strong for over 8 centuries. The result was a vertical city of over 150 rooms with kivas for ceremonies, towers for lookouts, and storage rooms packed with grain, all connected by a dizzying network of handholds, ladders, and low, narrow tunnels that forced any visitor to crouch in respect. This was a society designed for both community and defense, where every passageway was a calculated decision. Survival in this arid landscape depended on one crucial resource: water. The Ancestral Puebloans engineered a brilliant system to capture every precious drop. They built check dams and channels on the mesa top above, funneling rainwater into natural basins and down into reservoirs carved beside their dwellings. This was not a passive hope for rain. It was an active, sophisticated management of a scarce resource that allowed their community to flourish where others might have failed. The cliff alcove itself acted as a massive, natural climate control system. The massive overhanging rock provided shade from the brutal summer sun, while the south-facing orientation caught the low winter sunlight, warming the stone walls. This perfect placement created a temperate haven that stayed cool in summer and retained heat in winter, all without a single furnace or air conditioner. Mesa Verde stands as a stunning testament to indigenous engineering in North America. It was not about conquering the environment, but about listening to it, learning its rhythms, and integrating a complex society so seamlessly into the landscape that it almost disappears. This was a peak of sustainable living, a thriving community that understood a profound truth, that the greatest strength lies not in fighting your surroundings, but in becoming a part of them. Sometimes the greatest journey requires no movement at all. At Chartres Cathedral, a different kind of path was laid directly into the stone floor, a labyrinth over 40 feet wide that offered pilgrims a road to salvation without ever leaving France. Crafted in the early 13th century, this intricate circular maze is not a puzzle to be solved, but a single, winding path to be walked, a form known as unicursal. Its design is a masterpiece of sacred geometry, a complex pattern of 11 concentric circles divided into 4 quadrants, all laid out with nothing more than a compass and a length of rope. The stonemasons faced an extraordinary challenge, cutting 272 individual slabs of white and blue-black limestone to fit together in this precise, meandering course. Each stone had to be shaped to a unique curvature, locked into the floor so perfectly that the path appears as a single, flowing line. For the medieval faithful, this was a substitute for a pilgrimage to the Holy Land, a symbolic journey to Jerusalem accessible to everyone. A pilgrim would enter and begin the slow, deliberate walk towards the center, a distance of nearly 260 meters. The path doubles back on itself constantly, forcing a pace of patience and reflection. There are no dead ends, no tricks, only a single route that forces the walker to trust in the path itself. This was engineering in service of the soul, a physical manifestation of a spiritual belief that the journey, with all its twists and turns, is as important as the destination. Today, the stones are worn smooth by 8 centuries of footsteps, a testament to its enduring power. This labyrinth represents a profound truth about medieval engineering, that their genius was not always expressed in reaching for the sky, but sometimes in drawing a perfect contemplative circle on the ground, turning stone into a prayer. Within the humid jungles of Java, a man-made mountain rises to meet the sky. The Borobudur Temple, constructed in the 9th century, is the single largest Buddhist monument on Earth, a breathtaking fusion of spiritual vision and Stone Age engineering. Its builders assembled this colossal structure from over 2 million blocks of gray volcanic andesite, all without a single drop of mortar to hold them together. Instead, they perfected an interlocking system of knobs, indentations, and dovetail joints, locking each stone to its neighbor with a precision that has withstood more than a millennium of tropical storms and earthquakes. This was not mere stacking, it was a 3-dimensional stone puzzle on a staggering scale. The temple's very form is a map of the universe, a physical representation of Buddhist cosmology. 9 stacked platforms rise in a perfect step pyramid, with 6 square terraces below and 3 circular ones above, all culminating in a grand central dome. This architectural journey guides a pilgrim from the base of the earthly realm, through the world of forms, and finally to the formless realm of enlightenment at the summit. Every step upward is a symbolic progression towards nirvana, making the architecture itself a sacred text. This spiritual narrative is carved directly into the stone. Nearly 1,500 intricate relief panels line the walls, depicting the life of the Buddha and his previous incarnations with astonishing detail. Master sculptors worked for generations, transforming 2 miles of solid rock into a continuous visual epic, a stone library of teachings accessible to all. But the true engineering genius of Borobudur lies in its hidden defenses against its greatest enemy, water. The tropical climate brings torrential rains that could easily wash away an entire hillside. The builders integrated a sophisticated drainage system directly into the temple's design. Each of the 9 levels is slightly angled to channel rainwater inward, where it flows through hidden conduits and out through 100 beautifully carved gargoyle-like spouts. These waterspouts are shaped as the heads of mythical creatures known as Muqarnas, turning a practical necessity into an artistic flourish, a stream of stone beasts guarding the temple from erosion. For centuries, this colossal masterpiece was lost, buried under layers of volcanic ash and a blanket of jungle vines, a sleeping giant of human achievement. Its rediscovery and restoration reveal a profound truth, that the medieval mind could conceive of a universe in stone, balancing the cosmic with the practical in a harmony that still takes our breath away. While stone labyrinths offered spiritual journeys, other medieval structures enabled a far more worldly kind of travel. The stone bridge of Regensburg was a revolutionary feat of civil engineering that physically connected a continent. Completed in 1146, this bridge over the mighty Danube River remained the only fixed crossing at the city for an astonishing 800 years. Its construction was a battle against one of Europe's most powerful rivers, a challenge the builders overcame with a brilliant temporary technology, the cofferdam. Imagine creating a dry work site in the middle of a rushing current. Workers would drive a double wall of wooden planks into the riverbed, then pump out the water trapped between them. Inside this temporary dry chamber, they could lay the stone foundations for the bridge's piers directly on the river bottom, safe from the relentless flow. They repeated this daring process for all 16 of the bridge's massive arches, a testament to both courage and coordination. The bridge's iconic humpback profile was a masterclass in multifunctional design. That elegant curve was not merely for beauty. It provided vital clearance for boats to pass beneath during high water, while its arched form was inherently strong, channeling the immense weight of stone and traffic down through the piers and into the sturdy riverbed. This was a structure designed to work with the river's power, not just resist it, but the stone bridge was more than a passage, it was a fortified gateway. A formidable bridge tower guarded its entrance, serving both as a defensive stronghold and a toll station, controlling the flow of people and goods that were the lifeblood of medieval trade. The revenue from this traffic was so significant that it funded the construction of a city hospital, transforming this engineering project into a powerful engine for civic good. Perhaps most staggering of all was the speed of its creation. The entire bridge was finished in just 11 years, a blink of an eye for a project of this scale in the middle of the 12th century. This rapid success made Regensburg a nexus of commerce and a model for all of Europe. Its design was so admired that it directly inspired one of the most famous bridges in the world, the Charles Bridge in Prague. The stone bridge stands as a powerful reminder that the greatest medieval marvels were not always castles or cathedrals, but the humble, vital links that bound communities together and set the stage for the world we know today. As the medieval era reached its twilight, builders were still pushing stone to its absolute limit. The Bell Harry Tower at Canterbury Cathedral stands as one of the final, glorious flourishes of Gothic engineering, completed in the year 1503. This was not a project of cautious conservatism, but a bold final statement, a perpendicular Gothic spire soaring 72 meters into the English sky. Constructing such a tower on top of an existing cathedral, one that was already centuries old, was an act of breathtaking confidence. The primary challenge was one of weight and integration. How do you add a colossal stone crown to a building without bringing the whole structure down around it? The ingenious solution lay in 4 massive internal pillars, strategically placed to channel the tower's immense load straight down into the cathedral's most robust foundations. These pillars were not crude additions, they were masterfully woven into the existing architecture, becoming a seamless part of the cathedral's skeleton. The real magic, however, happens when you step inside and look up. Overhead, the ceiling explodes into an intricate web of fan vaulting, a lace-like pattern of stone that appears impossibly delicate. This was the pinnacle of the stonemason's art, where ribs of limestone spread out from slender columns like the veins of a petrified leaf, creating a canopy that seems to float without any support at all. Achieving this ethereal lightness required immense physical effort. The entire construction site was a forest of timber scaffolding, a temporary wooden skeleton that climbed higher than the tower itself. To lift the heavy blocks of prized keen stone, engineers employed sophisticated hoisting mechanisms, likely massive treadwheel cranes powered by teams of men walking in a giant hamster wheel, inching each precisely cut block into its permanent position hundreds of feet in the air. This tower represents a perfect marriage of brute strength and exquisite artistry, a final, defiant proof that medieval builders had reached the very peak of their craft. It is a bridge in time, a Gothic masterpiece completed just as the Renaissance was beginning to dawn, standing as a permanent reminder of what could be achieved when ambition was matched by 1,000 years of accumulated skill. Deep beneath the sun-scorched deserts of Persia, an invisible river flows. This is the magic of the qanat, an underground aqueduct so brilliantly conceived that it turned barren lands into gardens. While its origins reach back over 3,000 years, it was during the medieval Islamic era that this technology was perfected and spread, becoming the lifeblood of entire civilizations. A qanat is a masterpiece of patience and precision. It begins with the discovery of a water-rich aquifer at the foot of a mountain. From there, a master surveyor would plot a gentle, downward slope, sometimes stretching for 30 miles or more. The actual construction was a monumental underground endeavor. Teams of workers, known as Muqarnas, would dig a mother well at the aquifer and then begin carving the main tunnel backward toward its destination. They used the simplest of tools, plumb bobs to check for vertical alignment and water-filled channels to ensure their path maintained that perfect, almost imperceptible gradient. The genius of the design is in the vertical shafts. Every 60 to 100 feet, the Muqarnas would dig a shaft straight down from the surface to meet the tunnel they were carving below. These shafts served a triple purpose. They provided crucial ventilation for the workers deep underground. They were the only way to remove the immense quantities of excavated soil and rock, and once the qanat was complete, they became permanent access points for cleaning and maintenance. This system was not just engineering, it was a social contract. The water flowing through a qanat was a shared resource, meticulously allocated by time to different farms and families, ensuring no one person could hoard this liquid treasure. It created a ribbon of life in the desert, with lush fields and bustling towns appearing along its course, all fed by the cool, clean water that traveled safely underground, protected from the blistering sun and from evaporation. The qanat did not merely support cities, it birthed them. This technology became so vital that it traveled the Silk Road, reaching as far as China and North Africa. And in a testament to its perfect design, thousands of these ancient subterranean channels are still in use across Iran today, a sustainable water system that has quietly nourished the land for centuries, a hidden river of life flowing directly from the medieval mind. From the hidden rivers of Persia, we move to a fortress of fire and brick. Malbork Castle in Poland is not merely large, it is the largest castle on Earth by land area, a sprawling brick city built by the Teutonic Knights starting in the 13th century. This was their capital, a statement of power forged from millions of hand-fired bricks, a material that required a staggering industrial effort. Brickmaking became a seasonal siege against nature itself, with clay dug in the summer, shaped into forms, and then slowly fired in vast temporary kilns that dotted the landscape, all before the harsh winter frosts could halt the work. The castle's defensive genius lay in its layers, a brutal puzzle of concentric walls, deep moats, and towering bastions. An attacker who penetrated the outer gate would find himself in a deadly maze, trapped between rings of fortification and exposed to crossfire from every direction. Yet within these formidable walls lay a world of surprising comfort and sophistication. The great refectory, the hall where the knights gathered, is an engineering marvel in its own right. Its ceiling stretches an incredible 15 meters across without a single central pillar for support. This seemingly impossible span was achieved with a complex web of ribbed vaulting, a stone skeleton that distributed the immense weight of the brick roof outwards to the massive walls, creating a vast, open space for ceremony and gathering. Even more remarkable was the castle's climate control. The knights revived and perfected an ancient Roman technology, the hypocaust. Furnaces stoked by servants in the cellars would heat air, which then circulated through a network of clay ducts and pipes embedded within the castle's very walls and under its stone floors. This radiant heat transformed the cold, damp fortress into a livable palace during the long Baltic winters, a luxury almost unheard of in other medieval strongholds. Malbork was a complete, self-sufficient world. It housed a permanent garrison, extensive workshops, and immense granaries, all administered with the meticulous efficiency of a military religious order. This castle stands as the ultimate expression of brick Gothic architecture, proving that medieval engineering could achieve both overwhelming defensive power and a refined, almost modern, standard of living for those inside its protective embrace. While European knights built castles of brick and stone, a different kind of engineering miracle was being carved into the mountains of the Philippines. The Banor rice terraces rise like giant stairways to the sky, a living landscape sculpted by hand over 2,000 years ago and meticulously maintained throughout the medieval period. This was not a single structure, but an entire mountainside transformed into a vast green patchwork of over 10,000 individual paddies. The genius of its design lies in its harmony with the land. The builders did not fight the mountain's steep contours, they followed them, creating a stepped profile that performs two vital functions. Each level acts as a barrier, catching soil and preventing catastrophic erosion during the torrential tropical rains. At the same time, this cascading structure forms the backbone of a gravity-fed irrigation system of breathtaking complexity. The lifeblood of this system is the water captured from the mist-shrouded rainforests at the very peaks. From there, a community-managed network of canals and bamboo pipes channels the water downward, distributing it with remarkable fairness across thousands of terraces. The flow is carefully controlled by a simple system of mud plugs and diversions, ensuring every single rice paddy receives its share. This was engineering as a shared responsibility, where every farmer was a custodian of the water for their neighbor below. Holding this entire system together are the retaining walls, built entirely without mortar. Skilled hands stacked stones and packed mud into barriers that have withstood centuries of pressure from water and earth. Their secret is not a magic formula, but a tradition of constant, careful maintenance. Each generation repairs and reinforces the walls, a never-ending cycle of preservation that has kept this agricultural masterpiece alive for millennia. The rice terraces are far more than a food source, they are a perfect, sustainable ecosystem. The paddies create their own humid microclimate, the water supports fish and snails that provide additional protein, and the system prevents the nutrient runoff that plagues modern agriculture. This is why they are often called the eighth wonder of the world, not for their size but for their wisdom. They stand as a powerful lesson from the past, proving that the most enduring engineering does not conquer nature, but collaborates with it to create something that nourishes both the body and the land for generations. The quest for height and light found one of its earliest triumphs not in France but in the north of England. Durham Cathedral's nave, completed in the year 1133, stands as a revolutionary leap in architectural thought. Here, for one of the first times anywhere, builders dared to span the main aisle with stone-ribbed vaulting, creating a skeletal framework that would change everything. This was not the heavy, tunnel-like stone ceiling of the older Romanesque style. Instead, they designed a lattice of slender stone ribs arcing gracefully overhead, a stone skeleton that carried the weight of the roof along predefined paths. This brilliant innovation allowed the walls themselves to become something entirely new, a three-story elevation that reached dramatically towards the heavens. The ground floor was defined by massive, round pillars. Above that, a gallery level provided space for overflow crowds during important festivals, and at the very top, the clerestory level was punctured with large, arched windows. This triple-decker design was a radical departure, creating a vertical momentum that draws the eye irresistibly upward. Those massive pillars in the nave are a story in themselves. They are not plain cylinders but are deeply carved with stunning geometric patterns, zigzags and chevrons spiraling around their girth. This was far more than simple decoration. The carving served a profound structural purpose, visually articulating how the weight from the vaults above was gathered and channeled down through the pillar. It made the invisible forces of physics visible to any worshipper who looked, a sermon in stone about strength and stability. The entire cathedral was built from local sandstone, quarried and shaped with astonishing precision. Each block for the vaulting ribs had to be cut to an exact curvature, locking together to form a perfect, self-supporting arch. This required a sophisticated understanding of thrust and counter-thrust, the constant push and pull of stone against stone. The outward push generated by the vaults was countered by the sheer mass of the cathedral's thick outer walls and by the strategic use of hidden buttresses. This delicate balance of forces has been tested for over 900 years, enduring wars, rebellions, and the relentless English weather, a silent testament to the builder's calculations. Durham Cathedral's nave represents that critical evolutionary step where engineering ambition truly began to prioritize light and height without ever sacrificing an ounce of strength. It was a prototype for the great Gothic cathedrals that would follow, proving that stone could be taught to soar. The thunder of cannon fire signaled the end of an era for the towering castle. At the close of the 15th century, the rules of warfare changed forever, and engineers were forced to rethink defense from the ground up. On the contested border between France and Spain, the Salses fortress rose as a direct response to this new reality. This was not a castle designed for grandeur, but a low, brutal, earth-hugging machine for war. Its revolutionary design marked a critical pivot from the medieval stronghold to the modern bastion fort, a direct ancestor of the star-shaped forts that would soon dominate Europe. The tall, majestic walls of older castles had become death traps, vulnerable targets for the smashing power of iron cannonballs. The architects of Salses solved this with sheer, brute thickness. Its walls were immense, up to 10 meters wide in some places, built from a resilient mixture of brick and stone. This composite material was a deliberate choice, as the brick's relative flexibility could absorb and dissipate the shock of an impact that would shatter solid granite into deadly shrapnel. The fortress itself became a unified artillery platform. Built directly into the heart of those massive walls were vaulted chambers known as casemates, where the fortress's own cannons could fire from protected embrasures. This turned the entire perimeter into a bristling porcupine of defensive firepower. But the innovations did not stop at the walls. A killing ground of deep, dry ditches and intricate outworks stretched out from the main structure, forcing any approaching army to cross a vast, exposed plain under a relentless crossfire. The ground itself, however, presented the greatest challenge. The fortress was strategically positioned to control a key pass, but this spot was a soft, waterlogged marsh. To anchor this colossal weight of brick and stone, the builders reached back to a prehistoric solution on a breathtaking scale. They drove thousands of wooden piles, great tree trunks sharpened to points, deep into the unstable ground until they hit a solid, load-bearing layer of earth. This dense forest of submerged timber created a stable raft upon which the entire fortress could rest, a hidden secret locking the stone giant firmly to the earth. Salses stands as a powerful testament to medieval ingenuity in its final hour. It proves that these builders were not bound by tradition, but were brilliant adapters, watching the horizon for the next threat and engineering a formidable, brilliant